engineering process. We're going to go through the engineering process, and then we're going to talk about another homework assignment. And we did the homework assignments because we want you to do something beneficial that ties into the workshop, but also that helps you get your credit. So please get your homework in. We're probably going to have a Monday deadline for the next set of homework. But let me talk about the engineering process. There are a lot of similarities. One big difference is going to be when you did the inquiry process, you answered a question. And with the engineering process, you're going to try to solve a problem. But you're going to go through a cycle, and you can see that you can read this for yourself. But in both cases, you know, you're going to ask yourself some questions. You're going to try to look at the constraints with the engineering process, but you're going to do research in both cases. It's important, if you're going to try to solve some problem, you really need to think a lot about the problem and do research and see how other people have attacked the problem, what have been their solutions, and then you're going to maybe hopefully come up with some idea that might make it better. And with an engineering project, you're not just making a model of something that's innovative that students have found somewhere, like an earthquake-proof building in Buenos Aires, and making a model of that particular building. No, they're not doing that. What they're trying to do is maybe make an earthquake-proof building that's easier to build, or quicker to build, or less expensive to build, or maybe even more effective in some way against earthquakes. So those are the kind of things they're looking to do with an engineering project. And then they're going to have to try out a plan. They develop a plan and try it out, but usually they're going to have to create something, maybe like a prototype, so they can test it. And one difference with engineering, another big difference is they're going to test it to failure. If they're doing a civil engineering type project where they're building some type of building, or like the building we just talked about a little while ago about the rooftop garden, they're going to have to test that. And that's not something they're going to test to failure like they would a bridge or a tower, because you want to know how strong it is. But they're going to have to build some models that are really done very well to scale and test them, and try to answer their question. If that was an inquiry project, but let's say we're going to see what material, you know, how can we keep buildings cooler? And somebody mentioned cost. How can we maybe reduce the cost of air conditioning? So we can reduce the cost by having better materials, or maybe a stronger roof, or whatever, or maybe a roof that would withstand tornadoes better, or hurricanes. But in that case, they're going to probably have to test the roof to failure and see how much force it does take to lift the roof off the house, or to break it. But ordinarily, they're going to look at that failure, and from that failure, they're going to try to analyze it and come up with even a better design and improve what they had, so they can make something that's better than anyone else has. You know, it's something new that people would want to purchase and build. So that's kind of what we're going to do with the engineering process. And later, we're going to talk a lot more about the process itself, and just like we did the inquiry. But first, we can go to the next slide. I want to explain what we're doing here. This activity we're getting ready to have you do is not necessarily an engineering project that's going to solve really anybody's problem. What this activity is used for is to see how you might guide your students as they are building something, looking at design of what they're looking at, the design that they've chosen to build, and how to maybe think about ways to improve the design. And it's a good practice leading up to them doing an engineering project. And depending on your grade level, you can see grade 3 through 5, 6, 8, or 9, 12, you choose which type of structure you want to build. Now, the last word on this page, on this slide, it says span, but really it should say height. Minimum height above that should be 40 centimeters. We're not doing a bridge. If you were doing a bridge, it would say span, but it's going to be a tower. And so what your task is to build a freestanding tower. And the definition of freestanding would be, you know, like a tower, I can just pick it up and move it. It's not attached to anything like the floor or the table, the carpet, not fastened to anything. It just holds itself up. It's freestanding. 3 through 5, you're just going to build the tallest tower you can build. That holds itself up. It doesn't fall over. We're not going to have any wind or anything going on. It's just going to have to stand up wherever it is. 6 through 8, you're going to build the strongest tower that's at least 30 centimeters tall. So your minimum requirement, it has to measure from its base to the very top 30 centimeters. And then we're going to put a piece of cardboard. I have my little pad. I'll show you that in a few minutes. We have a piece of cardboard we're going to put on top of the tower, and we're going to measure from the floor to the lowest edge of that cardboard. That's going to be considered the height of the tower with the cardboard on top of it. And then we're going to put mass on top to add weight or mass, and it's going to eventually, the tower's going to either fall over or collapse, and then it's the mass your tower held before it collapsed to see which one's the best, who holds the most mass, as long as it's 30 tall. High school, you have a formula that you're going to use, and it's not necessarily just how much mass it will hold, it's also how tall it is. So it says minimum span. Minimum height should be 40 centimeters. So to qualify, it's got at least be 40 centimeters from the base to the lowest point of the cardboard you're putting on top of it. And then you're going to add masses to it. And you got a formula there. You're going to get 1 point for each gram that the tower supports before it falls. And then you're going to add that to 10 points per centimeter high. So if it's 40 centimeters high, that's going to be 400 points plus the mass supported. If it's 50, that's going to be 10 times 50 or 500 points plus the mass supported. And that's how you determine your score. Okay, we can go to the next one. Teresa is going to send you a list of materials that you can use.
Yeah, she's already done it.
She already done that. A list of materials that you can use. And Judy, my closet's locked, so I don't have my string, but I don't have to show it, I don't think. But you're going to use string like a kite string or some type of crochet string is fine. But string, you have a certain amount of string you can use, and tape, just masking tape or painter's tape that's about 1 inch wide. It tells you the length that you can use. We don't want to fudge and use extra tape. Now in the classroom, when students do this, if they'll hand me a foot of crinkled up tape, I'll give them another foot of tape, or another half a centimeter or some half a meter or whatever, if they can show me that they've messed it up and they need another piece. But they shouldn't use more than what we've asked you to use. Popsicle sticks, and you might use I can't remember if we used a piece of paper or an index card. I think it was an index card this time. And they can use the index card in the construction of their tower. And straws. Straws vary a lot depending on if you get straws, wherever you get them. If you buy them a big box, a big case of them, they aren't going to be very substantial probably. But Hardy straws are pretty strong, and so are McDonald's. McDonald's, I think, are the strongest. And we're talking about straws that are regular length, not the Hardy's really long straw that they have. It'd be the shorter one, not the coffee stirrers, but the regular size straw. But if you want strong ones, McDonald's might be the place to borrow them from, or to get them loaned to you. I went to the McDonald's in Western Boulevard in Raleigh a few years ago and told them we were doing a competition. They gave me 10,000 straws. So you might get a lot of straws for your classes. Anyway, you're going to build a tower based on the criteria that we just showed you in the previous slide, using only the materials that are listed. You don't have to use all the materials, but typically the better towers have used almost all the materials. Use all the materials you can in that list. Then we want you to take a photograph of it, and want all this done by next Monday at noon. Now that's earlier, but we need time to put all the photos in and analyze them and things like that. So if you'll make your towers maybe sometime this weekend or something, but take a photograph of it, a good photograph at an angle where we can see everything.
And take a photograph before you start testing it.
Yes, exactly, before you've torn it up. But take a photograph when you're ready to test it. Now, elementary folks, when you get your tallest tower made, you can back off and take a picture of it, and that's fine. And all you're going to do is measure the height of the highest point. But yeah, take a picture before you've added anything to it. Be nice to take a picture with the cardboard sitting on top. And then you're going to send a photo to me if it's elementary. If it's middle or high, you're going to send that to Judy. Then you're going to test it.
Oops, sorry.
And be prepared to tell, and you're going to, when you send us the photo, tell us how much it held, how tall it was, and how much it held. We need to know both of those factors if you're middle or high. And then high, you can also calculate your score and all that kind of stuff. We also would like for you to, when it does fail, to look at it and see if you can figure out why it failed. We'd like to talk about that next time. The point there is when students build anything engineering, whether no matter what kind of project it is, or even if it's a biology project or chemistry, physics, civil engineering or electrical or whatever they build and test, if it fails in some way, they need to analyze the failure, because if they can correct that, it can even be better. And so we're going to talk with you about that next week. And that's part of what you do with your children and your students. If they're doing an engineering project, you're going to ask them questions about how it failed and how it can be improved and what they need to do to make it better. And then they can redesign it, make another prototype, and test it again. They also need to test it against standard, like what's already out there. If they're doing a bridge or a tower for real, and that's what they're trying to maybe build a bridge that's easier or cheaper to build, they're going to have to find out how strong real bridges are and how costly they are, and the dimensions. When they build their scale model, it needs to be realistic. Judy, anything else we need to tell them about the homework, you think?
I think that's it. Just make sure if you could get it to us by noon on Monday, we would really appreciate it.
Okay, so that'll be part of your homework assignment, and this will be clearer to you by the time we finish today's talk and get so when you come back in on session 5 next Wednesday, it'll be clearer why we've done this and everything. Okay.
Okay, so this is talking a little bit about ways that you
Yeah.
can measure
Yep.
to be things. Look in your closet to be able to find things. I mean, your pantry and various places to find things that have the weight on them, and start with the smallest possible mass. And if it will hold that, then I would take that off and add something that's a little bit heavier until either you've got your heaviest thing on there, and then you can start adding again the smallest thing on there to be able to catch up. So that way you'll be able to give us the mass that the tower can hold.
I think there's one more. Did this have animation, Judy? Is there one more thing on this one?
Two more
couple
things.
Yeah. And if the product that you put on top, and it'd be something that's in a can or boxed up or something like that, it's not going to get messy, but you're going to put that on top like Judy said, and most of the time it's going to say like 1 ounce, or it's going to have grams. You can write down the grams and keep adding, or put multiple items up there until it fills. But we want to know how many grams it supports. Saying if you have a little can up there that's only got ounces, you're going to have to multiply that by 28, because there are 28 grams in 1 ounce.
Okay. All right.
That's
So
okay.
we've already talked about the testing. When you're measuring the height, remember it goes at the lowest corner of the piece of cardboard that you have on there.
One thing we haven't told them, Judy, is last night we determined that you're going to put one piece of cardboard, just one thickness, one piece of cardboard, not postal board or postal paper or anything like that, an actual real piece of cardboard you can cut. We want you to cut a 15 centimeter by 15 centimeter. That doesn't show up in the slides.
And this is like cardboard that you,
like a paper box lid or something.
well, I think what
Corrugated.
we used before is like cardboard, like if you get something from Amazon.
Yeah,
Pick
that's
that up.
fine. Yeah, it's like a corrugated cardboard. And 15 centimeters by 15 centimeters square. And you're going to, before you add any mass to it, you're going to have to put that cardboard on the top of the tower. The tower has to support it and stand alone. And if it's not exactly level, your height's going to be determined by the lowest corner of that cardboard to the base of the tower, straight down. So it's from the bottom of the tower to the lowest point of that cardboard, and horizontal is good because it'll be steadier tower. You can steady the tower as you're adding things. You don't hold it. You can only touch it maybe with a finger on the side, and then you got to remove your finger. If it falls over, you're done, or if it collapses, you're done. Typically, they'll fall over. You might set it back up, try it just one more time, and see if it will take it. You maybe put the mass in a different location if your
Oops.
cardboard's not level.
Okay.
Okay.
All right. So we'll be talking about this next week, but you can go ahead and analyze it yourself, and then how you think it could have been made stronger. And then look at other strategies you may have used. All right, so we're going to stop the screen sharing there, and moving onward, since we tend to I need to pull it up. All right, so Manley. I've got to get the next one open. So we are actually going to talk a little bit about the engineering process of doing coming up with that testable question. And I've got to still let me give me Manley. Okay, sorry to keep y'all going in between. And we've talked about this a little bit, and Manley talked about that engineering practice. You're going to get this. I don't need to read it for you. The thing to remember is they're very similar, and very often we have, I was thinking as we were discussing the engineering process, that really that garden roof that we were talking about, it's almost more of an engineering project. If your goal is to be able to get something cooler, reduce the temperature inside, that's solving a problem. So that's really an engineering project. And we tend to take a lot of things that we think are scientific research, and they're really more of an engineering, but both of them need to have that background information. We have to be able to analyze the data along the way. So I'm gonna move onward. The things about engineering projects that are, again, they're a little bit different is they are solving a problem or are meeting a need that we already have. There may be a solution for that need or for that problem, but you think there may be something better that can be done. That this, yes, we've got, we can use this, but that really is, it's a pain to develop. It's a pain to use. I really think we could do it better. So developing a new method of doing something can be extremely important along the way and be a really valid engineering project. But again, determining how you're going to test and measure it is extremely important, and finding out when it fails. So some of the examples. Yes.
Let me interrupt you a second. I think of that rooftop garden, and one thing we didn't discuss last night is, one thing you'll have to look at is if you have a big garden up there, soil, and it's going to rain on it, it's going to get wet. What's the weight of that? It's like snow on a roof, sometimes they collapse because it's so heavy. Snow's a lot lighter than soil with water in it, And so when we have a downpour and that soil is really saturated and you got almost like 3 or 4 inches of water standing on the roof for certain areas, it's going to support it. So that's part of your engineering projects, overcoming, collapse of the building roof.
So I keep thinking of more and more things. So I'm going to move onward because we need to have some time.
Can you go back just a second, Judy? Just 1 second.
Okay.
They can look at these, and I can talk about these. I'm going to come back to these during session 5. We're going to look at this same slide, but these are just some examples. I think of them almost like North Carolina examples of some problems you might want to solve. And so look at those. They may give you some ideas and to get started with your students. Okay.
Okay. All right. What I would actually like you to do, and we said to share it with the chat, but there's so few of you, I would really rather you speak up because everybody doesn't watch the chat, to see if there's something that you do in your classroom that is actually an engineering activity that you may not have thought of before.
Judy, let me inject one thing here. Some of you are probably thinking, well, I don't teach engineering. I know it is part of STEM, but I teach science. And so a lot of times it might be a little hard to rationalize some things being taught in your class, but the example you just used of the rooftop garden, is so close to inquiry, also engineering, that you can tie the two together. And I'm sure everybody's looking for good ideas for the club to do and extracurricular activities and things for children to do. They really get turned on engineering projects. So whether you're teaching engineering per se in your class or not, the process is very important, and it is STEM. So back to thinking of something you do or can do to get more engineering involved in what you do.
At the end of my Force and Motion unit, I have my kids bring in Legos, tons and tons of Legos all around the room, and we borrow from everybody. And then their job is to make the most aerodynamic, fastest, longest distance car that they can make. And then we go outside and we have this really big long ramp that we let them loose and we time them and see their speed and discuss how their engineering process affected them. Was it too heavy? Was it too light? Was it lopsided? That kind of stuff, how the wheels affected it.
Mhm.
That's great.
You know, Science Olympiad used to have them out of Legos build a crane that they had to build that held a certain mass at the very end of the crane, so you could build a crane that could hold the mass the furthest out from the main tower. Things like, you know, a lot of good things you can do with Legos.
Yeah, so in the chat, there's a question about would a balloon or car activity work? And
Yes.
then there's also a comment on earthquake resistant buildings and toothpicks and marshmallows.
Well, the balloon in the car, if somebody, the whole idea there might be they're going to use a standard propulsion for the car, which might be a balloon of a certain size. You know, they might want to figure out a different kind of propulsion. I'll come to that in a second, but they're probably designing a car that will go the greatest distance with the same amount of energy each time. Or they might be designing a car that will reach get some distance the quickest. So it depends on what problem they're going to solve, you know, and they're going to have to be able to reduce friction in the car and all kinds of things like that. But one thing they're going to have to do is give the car the same amount of energy each time. And a balloon might not be the best way to do that, because the first time you blow up a balloon and let it go, it really has more force as it expels the air than at times after that. It kind of gets stretched. So typically with cars that you're going to propel some way, people usually have a standard propulsion system, like they might drop something that's a certain mass that's on a pulley system that pushes the car. So every time you, or maybe let it go down a ramp, that's the same length each time, that sort of thing. But yeah, there are a lot of things you can do with cars, engineering projects.
And then there's a couple comments on earthquakes. And one is about the toothpicks and marshmallows. And then Cody added doing a project-based learning, building earthquake-proof houses, testing them on shaking table, which I would love to hear, Cody, more about that. Did the kids shake the table?
So what the shaking table was, it was really just two books that were held together with bouncy balls between them. So it just, you shook the bottom book and it just moved the top one back and forth and side to side.
That's a very creative approach. Things like that are going to help us think about remote learning experiments.
Yeah, the first thing they're going to have to build is how to have an earthquake, you know, and it's going to have to be the same every time. And I've actually done that project before with designing the earthquake, the apparatus to simulate earthquakes. That was my specialty in undergraduate school, was earthquakes. I was a geology, earth science major. But anyway, but yeah, they got to have some way to make a standard earthquake, and then they got to have really good scale models that represent their designs. And they also got to do research to find out what other people have done to have earthquake proof. One of the first earthquake proof buildings was on a cylinder. They had a shaft down the middle of the building, was a cylinder, and the floors were round. And when it actually had a real earthquake, guess what? All the floors fell on top of each other, fell right down the cylinder.
There's another thought just added about creating solar ovens and thinking about the heat transfer process and atmospheric phenomena.
Right.
Just a
There's
great way to tie the science and engineering tightly.
There's an interesting activity that you can do with just a transfer of heat and the rate of cooling with taking drink bottles like water bottles. And if you've got a temperature sensor or a temperature probe or something that they can measure temperature, I was thinking trying to do it at home, they could possibly use like the temperature probes that they put a cover on them that they might have, and be able to measure the temperature of loss. But what we did when we did it, when I've done it in several teacher workshops, during the school year, when you're in air conditioning areas, you do heat, loss, where you put hot water in there and let it cool. But if they're going to do it when in the hot summertime, sometimes you can put cold water in there and see how it warms up and which will warm up the faster. Whether you've got a wet, which just by itself, you put a piece of cloth around it, or if you put like a wet piece of cloth, what will pull the cooling out. And that's looking at insulation. You can also have them build model houses and put a light bulb on top of it and see which stays cooler inside.
I've done that with beakers inside a house. They've had to build the houses, Judy. And I call it keep your cool. Everybody has to build a house. You have limitations on the size of the house, has to be the same, but they use different materials and thicknesses and whatever. And you have a beaker of ice water inside that's exactly the same temperature for everybody out in the hot sidewalk on a 90-degree day. And the temperature probe's great because it can plot the temperature over time, which is cool. Now, that same question somebody just asked about the solar oven, we can do a lot of activities that will help teach our children, but it might not be something you do a science fair project. Let's go back just to the solar oven idea. If you got an idea for a solar oven that's going to make one that's less expensive or that works better, it's got to, if they're going to turn this in to a science and engineering fair, it's not just going to be a demonstration of a solar oven or a demonstration of a house design. It's got to be, they got to be proposing a way to solve a problem, like how to make one cheaper or more dependable or more accurate or whatever. It's got to be something like that, not just a demonstration of a solar oven or a demonstration of some house design. It's got to be one that's better. So that's the whole idea.
Yeah, and Shannon added a enrichment idea about insulated containers and keeping things frozen for longer, which is, it's always a great challenge with the 5-day coolers. That's a personal challenge of mine because they don't last 5 days.
I haven't researched this, but those Yeti coolers that cost hundreds of dollars, that company has made a lot of money on coolers.
So Shannon, your idea could be great in looking at possibly virtual classes, and that you could give them the parameters to be able, that the size that the insulated container had to be, but they could use different materials as long as it was that size. And then maybe have an ice cube inside of it and give them, look at the size for the ice cube and see how long it would melt. So that's something that students could do at home with activities that would be readily available, that, and we may be having to think more and more and more about getting them doing science. In addition, the science fair may be something that comes out of the science that you have them do it at home. So anyway, I'm going to move onward because we really want to talk about designing that project, or that developing that need or problem that they're going to have. And the steps in the engineering design process, Manley's talked about it. The brainstorming in there is really important for students to be able to come up with new ideas. And right above that, specifying the requirements and constraints. That's also really important because we don't know if it's successful or not unless we know to what level it has to perform. So when Manley was talking about the towers, you test them until they fail. So that's the constraint, the requirements. It has to be a certain height. It has to be able to hold a certain weight. And anything above that is gravy. It's good, but it has to meet those requirements and constraints in order to be successful. And the building the prototype and testing it along the way. So when a student gets started, they're going to have to think about what is a problem we have or what is a need. They can think about needs that they might have, people around them. I had a student one year that they're from a rural area and his grandmother lived out in the country, and it was getting in her car and driving to the mailbox in order to be able to see if she had any mail. And that sometimes was an issue because she wasn't that mobile. So he'd actually developed a project that when the mailbox was opened and then closed, it would send us a signal to his grandmother's kitchen. And so that was his engineering project. Now, if he had done a little more research, there are actually some things out there, but he developed his own model and was able to talk about how he did it, how he tested it, and how he was successful. So he found a problem that, someone that he cared about had and developed a solution to it. And so that's a good way of getting your students thinking about engineering projects that they might want to work on. Once they find something, they have to write that problem statement that's very similar to that testable question that you did. So what is the need or the problem? Who has it? And why do we want to solve it? So with his grandmother. The problem was is she couldn't get to the mailbox very easily, and she didn't need to go if there wasn't any mail. Who had it? It was someone that was dear to him, his grandmother. And why was it important to solve? It was to make her life easier. So if you're doing that, you need to be able to think about what is that need for that problem. So some of the ones that Manley, these are some examples I think you've given. You want to talk about these a little bit?
Sure. And I'll go, I know we don't have a long time here, but let's see. Why don't we let the group pick one and see if they want to say something about it? If they like to, let's address one. Somebody can choose one on the chat and then we can talk about it. Which one you want? Everybody read them. I think these are good examples they can see. Judy, I was going to pick one kind of off the wall that's not one of these. I'll leave those up there, but had a student last year that was working on a project that I heard about, and what they were trying to do is get people to conserve water in their homes. And they were looking at it in two different ways, like they were maybe having some type of shower nozzle that would be a reduced flow shower nozzle, but they also thought about human behavior, that if they had something in the shower that would, like a recording that you could set that would kind of let you know how long you've been showering and how much time you had left, that could actually get people to take showers that were shorter. So part of theirs was to design some system that would first find out how long it would be a good shower. And then they realized that if they could reduce the shower by 1 minute in a certain size town, they could save so many gallons of water or whatever. And so they were, they had a recording, they had a system that they could hook into the shower system so that when you turn the water on, it would start and let you know how much time you had left and give you some countdown. So that was a nice thing. They could get people to take shorter showers. But the locker one, design some type of locker that would be easier to lock. Maybe it's a push button. It's going to probably have to be a whole different design locker, and we got them now. There are all kinds of push button locks for homes now that they're costly, but they're easier to operate than the tumblers that we have now. I guess nobody bid on those. Those are good ones to look at and think about, but
so when you're okay, so I'm moving on. I'm sitting here.
Go ahead,
So when you're actually working on a project, and your student comes to you with a project, the things that you need to think about when you're guiding them is, can you think of, if you're coming with, I can't even talk, sorry. Can you think of a better way to measure whether the solution is, if yours is better?
What is better? What is better?
Yes, which is better? Your solution or the one that they already have, because your goal is to find one that is better than what is out there, but you have to be able to figure out how to measure that to determine whether it's good or not. It's got to be safe, not only safe for the people that may be using your solution, but safe for your students to be able to build it. And we want to look at safety and disposing the material. So you want to look at, what are you using? What are you going to be developing with? Like fiberglass is a great insulator, but fiberglass has also got issues with, getting into your hands. So students are going to be using that. Then you're going to have to think about safety issues that the students would be involved in. So that's something you as a teacher, when you're reviewing the projects that students come to you, you need to think about, what are these safety issues? Have the students thought about them? And maybe getting another person to look them over, whether it's scientific or engineering, to make sure that you're not missing something that could possibly be a safety issue.
I think nowadays, Judy, with things the way they are, if you're using materials, what would be a good thought to have would be when this kind of product reaches the end of its life, how can it be retrofitted to even be better again? Or how can the materials be reused or reclaimed in some way?
Or
rather
recycled,
than being
yes,
disposed of? That'd be a good thought to have.
right. Having access to those materials and being able to get them, having enough time to be able to do the project that the student wants to do. And this is another time I'm gonna, get on my soapbox. We don't have science fair week. You really need to work with your student and developing a project through all the different steps and checking them so that they understand that science and engineering is not something you do in one day, but it's something that you develop that process over a period of time, and that it does have steps, and you need to check each of those steps along the way.
Yeah, and Katie put a question in about, do you find that cost of materials can be prohibitive in creating engineering projects?
Yeah, I think that depends what you're doing. If you're doing a model, a lot of times it's not nearly as costly. But if the students also think that you're testing materials against existing materials, a lot of times manufacturers and businesses will give you materials if you're testing them. So one thing to think about is you might be able to actually get models of this or whatever from some of the manufacturers. But that usually depends what you're doing. You can pick something to build that is going to be costly, but most of the time you can get around that.
There's a resource that a lot of people don't know about. Most of you have Walmarts that are not too far from you, and every Walmart has grant funds that they can give to schools and to organizations that apply for the funds. And so if you were to go in and talk about, especially if you're in a Title I school, talk about you're engaging your students in developing independent research projects, and they don't have the funds to be able to buy the materials, because you have a grant, and Walmart itself might have a lot of the materials that they might need or might be able to use, to see about filling out that request form and seeing if you can get funds there. And I think every Walmart has up to $5,000 that they can give out. Now, they don't give one person $5,000, they try to spread it out, but that's a resource that not everyone knows that's out there, but to be able to check on that. And coming back, I always ask you to check the rules and regulations before you encourage a student and say, oh, sure, that's a great project, to make sure that it's something they can do safely. I will say that most of your engineering projects have a lot fewer restrictions upon them than your scientific projects do. And I think Teresa just put out the ISEF rules and regulations and the forms that are in there for you to be able to pull down. So we're going to talk about those next week, which ones would be appropriate and how to get around from having everything on it. So if you're looking at the engineering testing strategy, we've talked about testing the failure for the towers. We need to look at whatever it is. We talked a little bit about testing if you did a rooftop garden, how are you going to test that? We talked about testing heat exchange. So whenever you do any type of engineering project, how are you going to test it and analyze your result to be able to determine which is the direction to go with a prototype, what is working, and how you can figure out what needs to be changed to be able to improve that model or your solution. Whether it's having people evaluate it, whether you're testing a temperature, whatever it is, but you need to determine, again, what is that criteria and how are you going to measure it, and how you know if this worked or you succeeded. So developing that project, and I'm looking at the time here, I've got
11 minutes.
about 11 minutes to talk about the project. Everybody for their homework is going to develop a research project. Now, this doesn't have to be 5 pages long. I would really rather it only be a page. You can give me the brief, directions of what you're going to do without going into every single step. You can say, and test it, using various methods. Because we'll be reading every single one of them. So we don't want to read something that's 5 pages long for every single one of them. A page is sufficient. But looking at your projects, every single project, whether it's research or scientific, has to have a research plan, and it needs to be written before experimentation, and it needs to be approved by whoever is supervising that student. So if you are the supervisor for the student doing a research project, you need to read that research plan before they ever begin experimentation. And the reason being is this is when you determine if this is something that is safe for the student to do, safe for those that are around them, if it abides by the rules and regulations, and what special assistance they may need or special approvals. So it's really important, and by doing that, you are protecting yourself and that you know what's happening. If it's a scientific inquiry project, it needs to address the materials they're going to be used, the data they're collecting, the analysis of the data, and those safety issues. Engineering, again, possible solution, development, those constraints, and testing. You can't have any results in these because it's written before you do the experimentation. It will, however, have your bibliography. So, and as you're developing that, the things we look at when you're guiding your students, if this goes back to developing the question or the problem, is it original? Can it be done? And then you start thinking about materials they're going to need, if they may need assistance to be able to find that. Safety issues that you're going to run into, how it's going to be tested. Now, you may have a student that comes up with a project that needs to have tests run that you do not have access to. There are a lot of people out there that will help you out if you just seek them. We have a teacher in Brevard, North Carolina, who started working, doing really some amazing research projects with her high school students about 8 years ago now, 8 or 9 years ago. And she has developed a network of being, if they're doing like a genetics project, she has people that she can send that have said, we'll do the genetic coding for that, whatever it is that you're doing, and send you back the results, that they volunteer to help out. And a lot of folks will be willing to assist you. You just have to figure out who you need to seek out and who you need to ask questions to. And Manley and I will be glad to help you, brainstorm who maybe could help you if you get stuck in something. You also need to think about where it's going to be done. Elementary students cannot do microbiology, growing bacteria projects, period. And that goes back to the students' capabilities of handling bacteria safely and the resources that they have in their schools and the training that, and I'm not saying about anyone specifically, but most elementary school teachers do not have a lot of scientific background in handling bacteria and microbiology projects. Now, as soon as I say that, I'm going to have an elementary teacher that's listening to me that was a microbiology major and knows all about this. But since we have to make kind of a grandfather rule covering the majority, so that's one of the things that we have said. Middle school and high school students cannot grow bacteria at home. That is not my rule. That is the rule from the International Science and Engineering Fair. So there are a lot of projects out there that students like to swab everything in sight and then grow out petri dishes. That's really a very risky project, much more so than working with a known bacteria that you have gotten from a source that like Carolina Biological or somewhere like that, because you have no idea what you're growing, and it may be something that could be very dangerous. But it's something kids love to do. The rules state it cannot be grown at home. It can be swabbed at home, permanently sealed, taken to school, to a facility that can handle growing bacteria projects, but not at home. Students can do projects, places, any kind of project in multiple different locations, whether it's home or whether it's at school, if they're doing it in a university, in a laboratory, an industrial setting, medical center out in the field. With our students at home, we may be having more 4-H type projects coming up because those may be things that they have available to them that you need to look at. When you're looking at that research project, that research plan, you need to look at, does this need an adult sponsor? Now, this is someone who is looking at things closer than just you who's approving it, but they need to have someone that is actually working beside them. Do they need to have a qualified scientist who is an expert in a particular field? Similar to like if you're working with animals, you need to have the approval of a veterinarian or someone who is an animal care expert sign off on a project. If they're working on potentially hazardous biological materials, then you're going to have someone who's an expert to sign off on those before they can start working on it.
Judy, I just want to give you the 5-minute warning.
5-minute warning. Thank you. All right. So moving onward. You're going to be getting a copy of the back of ISEF Form 1A, and it has the information on how to write a research plan. If you're an elementary school teacher, you're going to say, there are a lot of words on here for my students, and that is granted, but you can pull out what they need. It tells you the basics. It gives you specific instructions on how to do an engineering versus a scientific project. It gives you specific requirements if you are working on, they're working on a project that has special approvals that are needed before they get started. So I stress again, it's approved, written and approved before the experimentation. It may need to be rewritten. If they rewrite their procedures or what they are doing, and then they need to submit a revised research plan. So you as the supervisor will always know what they are doing, so that and you need to make sure your students understand that. If they decide another method may work better than what they have gotten approval in that research plan, they need to run that past you so that you can say, all right, using hydrogen peroxide in this experiment was okay, but using bleach is not, because bleach is a much more caustic chemical unless you have safety issues that go along with it. So you need to be aware of what they are doing if they change their minds. You always need to check the rules and regulations to make sure it's something that is going to pass muster to be approved and to get those safety issues along. And there, when you look at that ISEF form or the research plan, it will tell you projects that need to be approved ahead of time. And that's, you need to look at. You also need to include in that research plan the type of data that you're planning on collecting or what you're going to be measuring. And remember, that's your dependent variable, what you measure. You need to think about the controls that you have in place, whether they're large enough numbers for it to be valid. If you're doing a scientific, how many times do you need to be able to replicate that experiment? If it's engineering, does it just fail at this point one time? Or can you replicate it so that it fails multiple times or is successful multiple times instead of, I got it to work one time, so that's it. Making sure you've got the limited variables and how you're going to analyze it. And at the end of that research plan, the bibliography, remember that background research they did, needs to be listed on that research plan. Elementary needs a minimum of 3 sources. Middle school and high school, it's a minimum of 5 sources. And I don't care if it's, you know, what format it's written at, whether it's APA or whatever, but I do need to know what the source is. And remember, people can be sources. So if you go to one of the state agricultural agents, that can be an excellent source that you list, but you have to put the person's name down.
You're not doing bibliography for this though, are we? For the one they're turning in next week?
Right. You don't have to, you know, you can make up sources. No,
Yeah, for this
I
one.
don't care. If they are using a website, you need to have the full link to the website. And you need to be careful that, again, going back, Wikipedia, anybody can put anything out there. So it's not the best source. And the .orgs and .coms are not as good a sources as the .edus and the .govs. Google Scholar is your friend along the way. So, and when you get through writing your research plan, you need to go to the rules wizard. And ICEF has, and Teresa just put that in there, ICEF has a system that you go through with your research plan, and it will ask you questions. You answer those questions based upon your research plan that you've developed. And then once you answer all the questions, it will come up and tell you what forms are going to be required for your project. At the end of your research plan that you turn in to us, you need to list which ICEF forms are required for the project you do. You can do any, your research plan on anything you want it to be. It can be on the testable question you developed. It can be on an engineering project that you want to do. But you know, put at the beginning of that, it will have that testable question or your problem or your need. If you go back to what it has in Form A. So Manley is telling me I'm out of time. Here is your homework written out for you. And this you'll get a copy of this presentation again. You've got, all right, wrapping up, what is required, what we went over. We talked about that engineering build. You're gonna send the photographs to either Manley or to myself with data on your model. Elementary, the height, middle, and you're gonna talk, and high school, you're gonna look at the weight of it. Develop a research plan from your testable question or an engineering project. You can change that testable question, use something entirely different or your own engineering problem. Your procedures and how you're gonna test it, and that need to be in there. And it can be kind of a simplified research plan, but please put down what safety issues you may run into so that we are aware that you recognize there are safety issues and how you account for those. Answer the rule, make up a bibliography for it, but go through the rules wizard and list the forms that are required at the bottom of that research plan. So you do have a little more to do, but this will complete the homework assignments for us and help you get those 10 hours that you need to be able to get the full 1 CEU for the sessions. We can give it to you legally. Plus, it's a great experience. You will be modeling what you're going to be asking your students to do.
We'll
All
stay
right.
on if they got questions, Judy. We'll stick around
Exactly.
if people got questions.
So
Yes.
I am going to stop sharing my screen. Manley and I are here, and we can hang in case you have any questions.